welcome to Wednesday's edition of Cracking the Cryptic, where today we've got something really rather interesting for you. This is called Pythagoras Nightmare by Matthias J. Raives, which is a new name to me. And this, we're going to have to get on top of our Pythagorean triples, I think, to solve this puzzle. I've had a quick look at the rules. At least it's going to give me, it gives me some examples of Pythagorean triples, but basically these triangles in the grid we have to fill with real Pythagorean triples in such a way that the solution works. Apparently there are 12 triangles in the puzzle, so we've got 1, 2, I suppose that's 2 triangles there, so that's 4, 5, 6, 7, 8, 9, 10, 11, and the big triangle for 12. So I can count to 12, and I may need to count higher than that. We shall see. Couple of messages before I read you the formal rules. Very well done to more solvers who've managed to get through the Paint by Numbers Institute Sudoku pack over on Patreon at the moment. This is the doctoral pack, the really stellar one, from Panthera, the Asylum, and Grockles. And Odin Vold-Ing Thorson has solved it correctly, as has Justin Kidman, and the Mighty Salmon has also managed to do it. Very well done, Mighty Salmon, and also for having an amusing name. And happy birthday today. Happy birthday to Ray from your partner Megan. Now, Megan wrote to us to say that Ray's been basically watching since pre-pandemic days, which makes you one of the early adopters of Cracking the Cryptic, Ray. You definitely deserve a birthday shout out for that. I hope you have a super day with, of course, lots and lots of cake. Other than that, I think I've mentioned in the last couple of videos the stuff we've got going on around the channel at the moment. There is the fantastic video from Woofers ZFG yesterday, which we released, which goes through the solution to a puzzle I've dubbed the hardest puzzle I've ever seen, or the hardest puzzle ever or something. A couple of you questioned whether that could really be true. Let me tell you, it is. If you spent any time studying Adventure by Jon Schneider from the Galactic Puzzle Hunt 2018, I find it hard to think that anyone could disagree it's the hardest puzzle of all time. It is absolutely barbarically, brutally difficult. It will twist your brain up and make it want to shrivel. And I think I've done enough puzzles, certainly since then and in the meantime, to have a reasonable idea of what could be a very hard puzzle. That one is certainly up there, and Woofer ZFG's video, which goes through the solution in 10 minutes, is a head rush. Let me just describe it like that. So definitely check that out if you haven't seen it already. Other than that, we have got, if you finish this puzzle really easily, there is a classic Sudoku that linked under this video. Just go to the description, click on the link to Sam Cavnar-Johnson's classic Sudoku. That has a very neat little trick in it. So if you don't know the trick, you'll probably find that puzzle very hard. If you do know the trick, you really won't. And there's a video over on Patreon explaining all for anybody who is interested. Now, let's get on with Pythagoras Nightmare, and I will read you the rules. Normal Sudoku rules apply. The sum of digits along each edge of a triangle must form a Pythagorean triple, with the largest number of the triple corresponding to the sum along the hypotenuse. Hopefully I don't have to explain which side of a triangle is the hypotenuse. Everybody who watches Cracking the Cryptic will know that, I'm sure. There are 12 triangles in this puzzle. Some Pythagorean triples include the following, and the multiples thereof: 3, 4, 5, 5, 12, 13, 8, 15, 17, and 7, 24, 25. Okay, well, I would have known 3, 4, 5 and 5, 12, 13 and the multiples thereof. So that just means that you can have a right-angled triangle with 6, 8 and 6, 8 and 10. Gosh, and also presumably therefore 9, 12 and 15 would form a valid Pythagorean triple. I think Pythagorean triples, the formal definition is integers, isn't it? Integer solutions to right-angled triangles that are Pythagorean triples. I'm probably making a massive mathematical faux pas there, but I hope not. And I vaguely remember from school there's some formula you can use to derive them, Euclid's formula or something. But Don't ask me more than that. But I didn't know 8, 15, 17 was a Pythagorean triple. That seems unlikely, doesn't it? So what was that saying? 64 plus 225, 289. Yeah, okay, fair enough. No, that is one. And 7, 24, 25 as well. So there you go. We live and learn. Do have a go at the puzzle. The way to play is to click the link under the video as usual. Now I get to play. Let's get cracking. And the way we get cracking is I'm terrified of this huge triangle. I really, really don't want to have to think about that. So I'm guessing we probably start with this one. Now, well, I can tell you this is not a 3, 4, 5 triangle because it has 6 on one of its sides. So can it be a 5? No, it can't be a 5, 12, 13 triangle because the minimum those 3 digits could add up to would be 6. If we made these 1, 2, and 3, they would already add up to 6. So neither of these sides can be 5. Can it be 8, 15, 17? I realise this is not probably the most elegant way of solving this puzzle, but this is my way. 8, 15, 17. So that would mean, well, if these 3 digits, we can't make these 3 digits sum to 8, because we'd have to put double 1, and that will break the rules of Sudoku. We can make these 3 digits add to 8 if we make them 1, 2, 5, 1, 3, 4 not being available. So this would have to be 8. This would have to be 15, and this would have to be 17. Now, can we rule that out? Well, I can actually rule 1 out from here very easily, because if that's 1 and these have to add up to 17, we need to put 9 into one of them, and we can't put 9 into either because of this 9. So that's definitely not a 1. If this is a 2, then we need these to add up to 15, and they couldn't be 6, 9, so they'd have to be 7, 8. So 2, 7, 8 is one possibility. Let me just see if that... So that would make this one 5, and then this would have to add up to 50. Oh, well, okay, that immediately works, which is a bit terrifying, actually. So I'm going to allege that that is a valid way of filling this this triangle. So we've got an 8, a 15, and a 17. Yes, okay. So that either that's going to be right, or there's going to be a whole multitude of ways of doing this. And the reason I'm worried about that is that actually I've not even tested all of the sort of multiples of 3, 4, 5 triangles that could exist here. So you could have... Well, you can't have 6, 10... you can't have 6, 8, 10, can you? But, you know, you can't have 6, 8, 10 because this side of the triangle couldn't work. So we have to be in a land that's at least equal to 9, 12, 15. Now 9, 12, 15. See, it's really hard to just see that this doesn't work. Let me just play around with this for a second. If it was 9 along this side, then this side would add up to 12. This side would add up to 15. That couldn't be a 1 then, because this would have to be either 6, 8 or 5, 9, both of which would be ruled out. So if this is the 9 side, you'd have to do it like this. Now this side we're going for 15, aren't we? Which would have to be 5, 8. Oh, is this going to work as well? And then 9, we need this to be 12. So if that's 5, this is 6. That doesn't work. If this is 8, this is 3. I don't believe it. Okay, wow. This is not how to do this puzzle. Either that or this puzzle involves a lot of trial and error. Let me just double check this. 9, 12, 15. Wow. Okay, so we've already found 2 ways of this working, and I dare say there are more ways than that. So, okay. So how do we make this easier for ourselves? I can't... the small triangles, it feels like they're just going to be there to sort of disambiguate the huge triangles. Let me just think about those for a second. If you've got a small triangle, can you make 3, 4, 5 work? I was about to say no. Oh no, you can. Oh, you can actually. No, you can. Yeah, you can. Doesn't look like you can, but you can. You can 1 plus 2 on one side, that's 3. 1 plus 3 on the other side, that's 4. And 3 plus 2 on the hypotenuse is 5. So you can make 3, 4, 5 work. Which is, well, is that good or bad? Don't know. What about the other ones? 5, 12, 13. Can you make that work? You probably can't make that work. Oh, maybe you can. I was going to say, because you've got 13 on the hypotenuse and 5 on one of the short sides, you're going to have 4, aren't you? At that junction. You're going to have to go 4, 1, 9 to make 13 and 5. And then, and then that doesn't work, because 1 plus 9 does not equal 12. Okay, right, so 5, 12, 13 doesn't work. 8, 15, 17, I can immediately see that doesn't work, because the only way of making 17 is going to be with 8 and a 9, and the only way of making the 8 side work then is going to be with a 0, and that will definitely break the rules of Sudoku and the other side, which needed to add up to 15, so that doesn't work. So we're either looking at 3, 4, 5, I think, or some multiples thereof. I'm going to rule out 7, 24, 25, because I definitely can't make 2 cells add up to 25. And I'm going to trust that I've been given all the littlest Pythagorean triples. I suppose it's possible that there is something else, but that would be very mean if that's the case. What about multiples of 3, 4, 5 then? So could we have 6, 8, 10 on a small 6, 8, 10. So the short side is either 1, 5. Let's try that. 1, 5. 6, 8, 10. So if we're looking 10 on the hypotenuse, so we can't put 5 on the hypotenuse, or you'd have to put another 5. So we must be looking at 1, 9, 5. And that's 14. That's bigger than the hypotenuse. That definitely doesn't work. Okay. So can you do it with 2, 4? If you do it with 2, 4, 4, 2, and you need the hypotenuse to add to 10, and you need the other side to add up to 8. So that does work. Oh, okay. Sorry. Yeah, I've just seen that. That's just one. That we worked out over here. Well, over here, but we worked out that 1, 2, 3 worked as a way of filling a little tiny triangle. So it's just occurred to me, can I just multiply these numbers? So multiply it by 2, I get 2, 4, 6. So if I multiply that by 3, I would get 3, 6, 9. And that's 15 on the diagonal, 9 and 12. That is another Pythagorean triple. So I see. So actually, there are lots of options for these little tiny triangles. So we can't go higher than 15 though, can we? If we multiply 3, 4, 5 by 4, the hypotenuse reaches a size of 20, which I definitely can't do in 2 cells. So the small triangles in this puzzle are either 3, 4, 5, 6, 8, 10, or 9, 12, 15. And this one can't be 3, 4, 5 because it can't have a 1 on it. So this one is either... I haven't got these in my head at all. It's either 6, 8, 10 or it's 9, 12, 15. And okay, so do you know what goes on the right angle in those instances? I feel like you do. in the 10 version, you've got 6, 4 on the hypotenuse and 2 in the right angle. And in the 15 version, you've got 6, 9. So you've always got 6 on the hypotenuse. That's weird. Well, that's quite interesting. And then you've always got 2 or 3 at the boundary. Not the boundary, at the right angle. So this is either 2, 4, 6 or it's 3, 6, 9. Aha. And there's always a 6 in one of those two cells, which is quite cool. So, okay. Well, it's quite cool, but it's not really cool enough to make progress, unless I can limit some of these other triangles. That one... Yes, okay, so I need to look at the right angles, don't I? And if this one was pointing at a right angle of a small triangle, then I would know that it was the right angle would have to be a 2 or a 3. So it's something to do, I think, with the right angles of the small triangle. Now this right angle sees a 1, so that's a 2 or a 3. The only thing I'm slightly nervous about there, though, is it possible to make this... See, these cells don't see each other. So can you double 5 that diagonal, which I know was an option I looked at over here when I was thinking about whether you could have 1, 5 on an edge. And I ruled out 5 from being on the hypotenuse because I said, well, that would require double 5 to make 10. Well, this obviously can't be a 1 anyway, so this triangle that's not relevant for, but maybe it could be relevant. Hang on. Let me just think about this for a second. No, it's obviously nonsense. It's total nonsense because this is a shared sum, so you'd have the same number on both other sides, and that's never going to work. So I'm talking nonsense. That's good. I'm talking nonsense. So this is 2, 3. These squares, so there's a 6 in one of these two. Now, I don't know if I know anything more than that, though. And then, how else are we going to think? What other digits can we look at here? Oh no. Oh, how strange. Right, I had not seen this at all. Right, here is something weird. This massive triangle, look at the hypotenuse of it. It's made up of short... It doesn't look like it is, but it's made up of short triangles. The hypotenuse of this triangle is those two cells. The hypotenuse of this triangle is those two cells. So you can see what's happening is that actually these 6 cells of hypotenuse are made up of 3 little triangles hypotenuse is. And that means that... So that means this hypotenuse is divisible by 5. Because we know that we're in a world where we're looking short triangles, small triangles, always have a 5 or a multiple thereof on their hypotenuse. So this is a multiple of 5. Now, bother. I was just wondering whether I could conclude from that this big triangle was some multiple of the 3, 4, 5 triangle. Sorry, there's a bit of mower noise outside. Mowerick, as some of you like to call the person mowing. But okay, they're receding again. I think that's the farmer in the nearby field, plagued by farmers and pilots. Now, yeah. So what I was thinking was, now that I know this hypotenuse is divisible by 5. Can I assume that this triangle is a multiple of 3, 4, 5. Now, I was about to say, of course I can, but I've noticed that the 7, 24, 25 triangle is rather suspiciously, that has been given to me. Now, well, it's not going to be the 7, 24, 25 in its naked form, is it? Because I can't make one of these sides add up to only 7. So we're going to have to 1, 2, 3, 4, 5, 6. Oh no, actually, so it's not. No, okay. I think this has been given to me as a troll. Because if I multiply 7, 24, 25 by 2, I get 14, 48, 50. Now, although, well, that's totally broken as well, to be honest, because the minimum I could make 6 cells in the same column or row add up to would be the triangular number for 6, which is 21. So we'd have to be multiplying it by more, but the moment we do that, the other side has to add up to more than 45, which is impossible because of the secret. The secret, of course, is that any complete column, any complete row, or any complete box of the Sudoku contains the digits 1 to 9 once each, and therefore adds up to 45. So there's no way I can make only 6 digits add up to 48, or whatever the number was that I just got there. So that tells us that this triangle here, this massive triangle, is some sort of multiple of the 3, 4, 5 triangle. Now, and we know that the sides have to get to at least 21. So we must be looking at least a 7 triangle then. So 7 times 3, 7 times 4 would be 28. So perhaps this is a 21 in either here or here, a 28 either here or here, and then a 35 along the diagonal. But it might be able to be more than that. 8 times 3 is 24. There's that's not going to be prohibited in a 6-cell string. 9 times 3 is 27. 9 doesn't work because 9 times 4 is 36, and I can't make... Oh no, I can. No, I can. It's 5 digits I couldn't make add up to 36, so I could do 9. Oh. Okay, but maybe I can't do 10 then. No, I can't do 10. 10 times 4 is 40, and I can't make 6 cells add up to 40. Right, good grief. So this triangle here, we now know, is either 21, 28, 35 triangle, a 24, 32, 40 triangle, or a 27, 36, 45 triangle. You take your pick as to which of those you think is the most likely. Okay. Rather annoyingly though, I still haven't got a digit, have I? Oh dear, dear, dear. Come on, get a digit, you silly man. Does this triangle have to be symmetrical? By which I mean, those digits are going to be... Okay, yeah, they're the hypotenuse, aren't they? So whatever the hypotenuse is, it's going to force these two. I think those two cells must therefore be the same. These are the same. So... Oh, for goodness sake. This is why we've been given 4, 6 and 9. This is why we've been given 4. Look at these triangles. They have 4, 6s and 9s on the diagonals. Oh, Simon. So this cell cannot be 4, 6 or 9. And if that's true, and we know small triangles are basic triangles, so they're 3, 4, 5 or multiples thereof, and we can't put 4, 6 or 9 in this cell, this must be a 3, 4, 5 triangle. If it's a 3, 4, 5 triangle, it must have 1 in its right angle. 2 digits. Bang. Sorry, I suspect some of you have seen that a long time ago. So now... Oh, yes, I know what this is going to do. This is very clever, actually. Okay, so now you've got ones in these. These ones are looking at the other small triangles. So whenever we can get a 1 look there, this one sees this right angle. So that must be a 2 or a 3. Oh, yeah, look. And we know 4, 6 and 9 go on the hypotenuse, and 4, 9, look at that, that's a 6. So this is a 4 or a 9. I don't actually think I know which is a bit strange. So if that was 3, 6, 9, 2, 6, 4. Okay. Alright, but that means, yeah, look, oh, this is gorgeous. So this one sees that triangle's right angle. So that's a 2 or a 3. Which means we know there's a 6 on its hypotenuse, and that 6 can't go there by Sudoku. This is very clever. This is far, far cleverer than it has any right to be, actually. Now that's a 6, so this triangle must be a 2, 3. I'm getting loads of... I've got 2, 3 pairs all over the shop. 2s and 3s have to go into the bottom row here. Oh, lovely. Right, I haven't got a 1 looking at this triangle, but I have got a 2 or a 3 in its box, so this triangle can't be a 1, 2, 3 triangle. Or it can't be a 3, 4, 5 triangle, if you know what I mean, which would require the digits 1, 2 and 3, because then this cell would have no value. So this is a multiple triangle, which means its right angle is a 2 or a 3, which means it's got a 6 on its hypotenuse, which is now here, which means this square is 4 or 9. So now, look, now these, oh look, yeah, now these two squares are not 6s, which means we can place the 6 on that hypotenuse, we can place the 6 on this hypotenuse, we've got a 2, 3, 6 triple in the bottom row now by Sudoku. I've got the opportunity to put a 6 on this triangle at the top. Oh yeah, look, this one is looking at this right angle, so that's a 2 or a 3. I need to put 6 on this hypotenuse, and it can't go here, so it can go there. I was just checking that. It looked a bit dangerous from a Sudoku perspective, but in fact these do not see each other by the medium of Sudoku, so that's a 6. These are not 6. This is a 2, 3 pair. This is a 4, 9. Still don't think we know which. And this triangle now can't be a 1, 2, 3 triangle because it will break this cell again. So this is a 2 or a 3. Where does the 6 go on this triangle? It goes here. And this is a... Oh, this is nice. This one can't be a 9. So that's a 4, which means this is a 6, 8, 10 triangle. And that's a 3, and that's a 9, therefore, because this is a 15, 12, 9 triangle. And that's a 2. Oh, and this could go. This could go now. Because now I'm getting... Oh, no, it's stopped. Oh, no, it hasn't. No, it hasn't. 3, 9. So that's a 2, which makes this a 4. This is now a 2 by Sudoku, so this is a 3. This is a 2, so that's a 4. This is a 2, so this is a 4. Good grief. Now that's a 2 and that's a 3. And I want to say I've got... How many 2s have I got in the grid? Loads. Yeah, loads. I can get the 2 in this box. I can get the 2 in this box. And all 2s are now filled. I bet you I can do the 3s as well. 3 goes here by Sudoku. 3 goes in one of those 2 cells. Hang on, let's just get these 3s. That 3 goes in here. 2, 3. Oh, I've got 6 3s. Okay, maybe I can't get all the 3s. The 3 in this box is in one of those 3 positions. Let's check 4s, because we should have a whole panoply of 4s as well. 4 goes here. 4 goes here by Sudoku. Now I've got even more 4s than I had before. I've got all the 4s. 6s. I've just got all the 6s. Right, 1s. Oh, okay. Oh, no, that's good. I can put the 1 in box 3 there. 1 in one of 2 places only in box 1. 1 can be placed in box 6. 1's in a domino in box 5. 1's in a domino in box... yeah, look at that. That's big. 1's in a domino only in box 7. And that domino looks at that cell, which places the 1 on this triangle at the top, which was the hard triangle that I couldn't do at the start. So now... Okay, I'm not quite done with 1s. Okay, so... Oh, look, I know what I've done now that I hadn't realised until I just looked at it. Look, I have got the size of this massive triangle because its hypotenuse now adds up to 40. Which means we've multiplied it by 8. We've multiplied the basic 3, 4, 5 triangle by 8, which means the sides have to add up to 24 and 32, which is probably restricted. 24 and 32. So what have we got along the bottom here? We've got 15. That's very annoying. Oh no, I can't put 8, 9 in here. There's a 9 here. Oh, that's lovely then. Right, so this side of the triangle I don't think can add up to 32 anymore. Because it would need an 8-9 pair here to give me the 17 I need. And the 9 rules that out. So instead, this is the 32, which hopefully can add up. So I've got 17, 20. I need these squares to add up to 12, and they can't be 3, 9 or 4, 8. So these are a 5, 7 pair. And therefore these squares have become a 9, 8 pair. This is a 5, 7 by Sudoku. This 9 tells me the order. So that all gets filled in. We get 5s and 7s into column 8. We get 5, 7s and 8s into these cells. But no, okay, I need to not do this, don't I? I need to get this side. I need to sort this out. So I got 32 here, I'm multiplying by 8, so I need 24 here. And I've forgotten what I had, 15. So I need 9. I can't have 2, 7, I can't have 3, 6, I can't have 4, 5. This is a 1, 8 pair, and there's a 1 here. There we go, 1, 8. So this is a 1 by Sudoku. These cells are now known. I suppose they've got to be 5, 7, and 9. Don't seem to be able to do anything with that, somewhat surprisingly. Where does 1 go in this row? It goes here. Where does 8 go? It goes here. This is not an 8 anymore, so there's an 8 in one of those 2 at the top. The massive triangle is now basically done, just this 5, 7 ambiguity to sort out. This cell, I've got loads of 5s and 7s everywhere. There's probably some mathematical reason for that. So I guess what I'm going to have to do at some stage, this triangle, which is so weird. So this triangle is the disambiguating triangle. And I tried to start the puzzle looking at this triangle, so that was clearly an error. Okay, so we've got to go 5s, 7s, 8s and 9s along here. 5, 7, 8, 9, that's not 9. That's not 9. Oh, I see, 9 is here. Right, okay. So 9, let me just check 9s. Oh, look, 9s. I can definitely do more with 9s. In fact, yes, this is a 9, this is a 9, and that's going to give me, I think, all of the 9s. That's good. So, therefore, we've got where does 8 go in the middle box? It has to go here by Sudoku. Unsurprisingly, that leaves the 5, 7 pairs up this column. It gives me a 3, 8 pair, which is interesting, look, in box 2, and a 5, 7 pair here. So this is 3 or 8 on the right angle of this triangle. And probably what we should do is work out what we've got onto the hypotenuse here, and then we can probably narrow it down. So it's 5 7s and 8s everywhere, isn't it? 5 7 8. This has got to be 5 7 or 8. No, this is 3 5 or 7 over here, because we've got the 8 in this row. So that cell, oh no, that cell is 5 7 or 8 because it sees the 3 here. Oh, so okay, so I can make that. This is going to be, is this going to be a multiple of 3? Did we work that out? Or no, we didn't. We didn't. We worked out, didn't we, that I was going to say, I think I worked out that there was a way that this worked with 8, 15, 17. I may be misremembering that. But here is a beautiful, oh, that's just, Matthias, take a bow. This is a beautiful puzzle. That's not an 8. And the reason it's not an 8 is nothing to do really with Pythagoras. Well, it's a little bit to do with Pythagoras. But if this is an 8, it forces the hypotenuse to have a 5 and a 7 on it, to which we will add this digit. So the hypotenuse size is 12 plus red. But this side of the triangle, its size is 8 plus 6 plus red, which is 14 plus red. So that would be suggesting that this side is longer than the hypotenuse, and we know that's never going to work. So this has to be a 3, which means that's a 3 and that's an 8. Oh, please, that must do something good, does it? Oh, it gives me a 3 down here. I don't know. I think I'm still going to have to do the maths on this to actually figure it out. Have I done all 3s now? Yes, I have. So I'm just left with loads of 5s, 7s and 8s. Oh, but this side has to be quite small now. Right, let's check whether the 8, 15, 17 version of the triangle was the one that I was very worried about. Have we got an easy way of... Okay, or maybe the simpler way is to look at this side, because this side really does have only 2 options. We're either looking at 14 or 16. 14, that is not a multiple of anything we've seen before. No. Okay. Well, unless this is a 48 side, which it's not. So actually this must, I think, be 7. And that gives us a 16 side. And 16, well, we can rule out that this is a 16, 30, 34 triangle for obvious reasons. So this must be a 16 because we're multiplying the 3, 4, 5 triangle by 4, which means that this needs to be 12, which means this needs to be 8, which means this should be 20, and that requires that to be a 5. And I think that that is the only way that works, which gives me a 5 here, a 5 here, a 5 here, a 7 here, a 7 here, 7, 5. And is this just going to go through the grid now? I think it should do. That's a 7, that's a 5, that's an 8, 5, 7, 7, 5, 8, and then we put 7 in here, and we click tick, and that's how to solve the puzzle. Wow, that's just so clever. Matthias, that is so clever. I think a lot of people who enjoy maths are going to absolutely rave about this puzzle because it's really, really beautiful. And it's so strange that it has a... It's so strange you've managed to put a logical solution path into it, because it doesn't look like it should have one. I was a bit worried that it was just going to be a whole sequence of trial and error at the start to try and narrow down the triangle, especially this triangle. But it's not at all. Once you appreciate the power of the geometry, you can actually work out an awful lot about this just by focusing on the tiny little triangles. So I hope you enjoyed it. I hope you had a go. And we'll be back later with another edition of Cracking the Cryptic.